not made for digital modes. So digital modes did evolve over time, and people realized that they need to build interfaces and adapt it to the ham radio. So digital modes are handled in a particular way. The radio is an analog radio. It's meant for voice. So the only kind intelligence the radio can handle is analog intelligence. To operate a digital mode, we unplug the microphone. To the microphone input, we'll plug in a device called the terminal node controller, something like this. What a terminal node controller is doing, it will gather and standardize digital intelligence. But digital intelligence is created by the operator who is typing on a keyboard. By typing on the keyboard, a digital code is launched. The most usual digital codes are 6-bit and 7-bit codes. The 6-bit code is the Baudot code, introduced by Émile Baudot, a French telegraph engineer. Later on, the 7-bit code gained worldwide acceptance, and this one is called the ASCII, American Standard Code for Information Interchange. The ASCII code has a 7-bit and an 8-bit version. So the 7-bit version is the truncated ASCII code. It has 128 combinations. That includes all of the punctuation numbers and the whole alphabet and other characters. The 8-bit version of the ASCII code has 256 combinations, so most of those combinations are commands. Now, those codes, one or the other, is launched by the human operator by typing on a keyboard. The codes are gathered one code after the other in groups. The terminal node controller is doing that. So the digital intelligence which is created on a keyboard, the keyboard nowadays is the keyboard of a computer. But in older times we did not have to use a computer, we used a teletypewriter. So the teletypewriter created the 6-bit Baudot code. Whichever version of the code is, finally there are digital bits, high and low bits, and those high and low bits must be grouped in groupings of 2 or 3 or 4 or many more. So each time we have a grouping of bits, this group is led into a next device called a modem. And the modem is a modulator-demodulator. What the modem is doing, it would interpret the digital bits and would turn the digital bits into audible audio frequency tones. Those audible audio frequency tones, then they enter the microphone input of the radio, and from there it's being transmitted as if it was voice. Now one up, please. A few examples here for binary coding. A binary code is a succession of zeros and ones. This is almost similar to Morse code. Why is it that this could not be Morse code, by the way? I snapped this out of a posting of the internet. Well, there are proportions to Morse code. And the dots and the dashes are in a 3-to-1 ratio. Here there only are 2 high bits. So Morse code would have longer dashes. Anyways, each time a binary 0 or a binary 1 is being sent to the modem would associate a packet or a grouping of cycles. This cycle this time is called the amplitude shift keying. Why amplitude shift keying? Because the amplitude is known. There is no audio frequency tone when a 0 bit is present. And then the amplitude jumps to its maximum value, jumps or shifts each time a 1 is coming. So in binary amplitude shift keying, each high bit is associated with an audio frequency tone, and each low bit or 0 or false logic level is associated with no signal. A little up, please. Now we look at binary frequency shift keying coding. In frequency shift keying, both the zeros and the ones, they cause the radio to receive a tone. The tone could be a higher frequency and a lower frequency, such as 600 Hz and 1000 Hz, for instance. Both are audio frequency tones well within the range of the transmitter. So there is a lower frequency for a 0, a higher frequency of a 1, and you can pick out how there were two 1 pulses. There is a wider section on the horizontal axis here where we have those audio frequency tones. So opposite amplitude shift keying, certain digital modes, they use frequency shift keying. So the frequency is hopping back and forth each time a 1 and a 0 is coming. Now underneath there is an example for binary phase shift keying. See how ones and zeros, which they are above there, would cause the phase to suddenly change. See how an audio frequency oscillation suddenly ends and then the oscillation reverses. When the oscillation reverses, then in that instant there is a 180 degrees phase shift. So binary shift keying, frequency shift keying, and amplitude shift keying are all illustrated here. Let's go a little further. The next slide, please. Here we have an illustration of quadrature phase shift keying. Now in quadrature phase shift keying, the terminal node controller grabs two bits. Those two bits, one after the other, they could have only one of 4 different combinations. 2 bits, they both could be zeros, or one could be a 0, the other one a 1. Both could be a 1, or one could be a 1 and a 0. So each time a 0, 0, 0, 1, 1, 1, or 1, 0 is coming, again, you type something on the keyboard. Whatever you type creates digital codes. Digital codes, they have bits. Those bits, they go to a terminal node controller, and the terminal node controller groups them, 2 or 3 or 4 or many, and each time 2 or 3 or 4 bits are grouped, there is a number of possibilities. For 2 bits, 2 to the second power is 4. Altogether there are 4 different possibilities, so the phase is being shifted 4 different ways. This is illustrated with a phase crust, because sinusoidal oscillations, they do have a phase, and if we do a time domain representation, this is something you would capture on the oscilloscope. Underneath here we have a vectorial representation that shows that there are 90 degrees increments. So imagine that in the old Navy, a sailor was on the top of the mast and had flags, and it was convenient to hold the flag up or one way, the other way, or down. And at a certain distance, the other operator on the mast of the next ship with a binocular could read those angular positions. So this was the beginning of data communications with quadrature phase shifting. Now the quadrature is a phase quadrature of electronic signals. Next, there is an 8 phase modem phase cross illustrated. There the terminal node controller gathers 3 bits. 2 to the third power is 8. So with 3 bits, if all 3 are 0, 0, 0, 0, all the way to 1, 1, 1, there are 8 different combinations. To represent those 8 different combinations, the phase is shifted in 45 degrees increments. So what's going on here, that we have 3 bits per signal, or 2 bits per signal. The signal is being sent into the microphone input with a given rate. The signaling rate is the rate at which the analog tones are changing. This rate is called the baud rate. So the baud rate, after the name of Emile Baudot, the baud rate represents the number of analog changes at the input of the analog channel. The bit rate represents the number of bits per second that they are flowing down from the intelligence generator. So the baud rate is always lower than the bit rate. If there are 2 bits for one signal, then the baud rate is half the rate of the bit rate. If there are 3 bits per one signal, then there will be 3 bits per baud, meaning that the baud rate is 1/3 the rate of the bit rate. So now we can generate bits with a given speed. Computer telephone modems, they are known to gather as many as 14 bits. So there would be 2 to the 14 combinations, which would be into the thousands, and all of those combinations, they represent audio frequency tones where both the amplitude and the phase is changing, because we are running out of possibilities. And if all of those many thousands combinations are illustrated, a very complex phase cross would result. So we like to just represent the very tip of each phasor, and those tips are called stars. So you look at this diagram and you ignore everything else but only see the blue crosses. What you see is the stars in a galaxy. So modems are characterized with their star diagram. Okay, let's go further. Those were just a few illustrations of possible modulations. Before I explain this, I want to recap that there are commercial applications in digital modulation and commercial applications in data communications. What's the difference between digital modulation and data communications? Do we have these both in ham radio? Yes, we do. Now we have a new D-star repeater in town. D-star is the property of ICOM. The ICOM radio company developed it, but roughly it's functioning in a similar fashion as the telephone company. At home, you talk to your telephone. The microphone is connected over 2 wires into the telephone office. In small town, Sault-Ste-Marie, there are approximately 200,000 telephone lines. We have more telephones than people in town. So each 200,000 telephone line ends in an analog to digital converter. Where there is a telephone, there is an analog to digital converter. You talk to your microphone, your analog voice is converted to an electric wave. That electric wave runs down on a wire pair into the telephone office, into the analog to digital converter, and the analog to digital converter takes samples from your analog voice, converts those samples to an 8-bit code. Well, this is how a D-star is functioning. A D-star radio, you talk to the microphone, and immediately next to the microphone there is a analog to digital converter that creates 8-bit codes. It takes samples of your analog voice. Now the encoding for the telephone company and the encoding for D-star radio is different. Nevertheless, when analog intelligence is converted into bits by an analog to digital converter, then this digital intelligence will modulate the radio frequency carrier. In the case of the telephone company, that radio frequency carrier is a light wave, a laser beam. In the case of ham radio, then the analog carrier perhaps is a 146 megahertz VHF radio frequency oscillation. So this was digital modulation. Digital modulation converts analog intelligence into a digital format. Opposite to this, digital modes in ham radio, they eventually transmit text messages. The operator would type something on a keyboard. It generates bits. Those bits are converted to audio frequency tones, and those audio frequency tones, they enter the microphone input. So that's the difference between digital modulation and data communication. Digital modulation in ham radio is very recent. The Yaesu company and the ICOM company, they both developed their proprietary versions. Now about this, the transmit-receive switches. This will pop up as a test question somehow for your test. When we have a microphone at hand, the microphone has a push-to-talk switch. You push that switch and you talk. But what's happening in the equipment? As you push your microphone switch, you have to kill your receiver, because when you talk, you do not want to hear the noise. The noise would then acoustically couple back into the microphone. So push to talk, you need to kill the receiver. So the push to talk switch is connected into the receiver, or the receiver is powered off for as long as you are talking. In the same time, the transmitter must be powered, because when you only receive, you don't want to transmit. You want to transmit when you squeeze the push-to-talk key of the microphone. So the push-to-talk key turns the receiver off, turns the transmitter on. And now you are talking, and your intelligence goes into the modulators, and then you modulate and amplify that signal, and you transmit it away. But you want to send that signal to the antenna. So we have another function for the push-to-talk switch. The push-to-talk switch must control an antenna relay. The antenna relay switches back and forth, connects the antenna to the output of a transmitter or to the input of a receiver. Now imagine that you have a transmitter in one box and a receiver in another box, and then the two may have their own independent coaxial cables, and those two coaxial cables, they both could run up the top of the tower where there is an antenna relay, and very often this is how it's done. However, when you have a transceiver, a transmitter and a receiver both in the same enclosure locally, then this switch is eventually inside your transmitter, and there is only one single coaxial socket, and one single coaxial cable is going up to the tower and connects to the antenna. So this switching can be done down in the transceiver or right up on the antenna if you have separate transmitters and separate receivers. Both cases are widely used in ham radio. Lots of home brewing on the VHF, UHF, and microwave bands uses the format of a separate transmitter and a separate receiver, and the antenna relays are up on the mast. One next, please. This is just a view of a typical coaxial relay. A coaxial relay like this, if you buy it used second-hand or surplus on eBay, it could cost as low as $20. A whole new one could cost well over $100. Coaxial relays, they come with every imaginable connector. Those are N connectors. N connectors were invented by an engineer named, what was his name? Ney. And his name was borrowed to designate this fine UHF frequency connector. Okay, so this is just a possible coaxial relay. There are many other formats, and there are solid state ones. As one is coming up next, is the next illustration. I hand copied this right out of your manual. This manual, and that intrigued me. Why would they ever put this complex solution into? And because you have those manuals and you may read through and you wonder how it works, then I am not sure if this will come up as a test question, but it's easy to deal with. There are two diodes. What we need to know about diodes: when diodes are forward biased, from the standpoint of alternating current, AC currents, they can flow both ways through a diode. So if we apply a positive 12 volts with a current limiting resistor to the anode of this diode turns on, and because it's right parallel across the receiver, it would short out the receiver. So reception is not possible. But the positive 12 volts through the inner core of the coaxial cable is led to this transmit diode. Well, this does not short out, it just turns on. Once this diode is on, you can transmit through it backwards and forward. So alternating currents, radio frequencies can go through this diode. Now, because the received diode is a dead short circuit to the ground, each coax section there is a quarter wavelength section. And you know, a quarter wavelength transmission line short circuited at one end is an open circuit at the other end. This by itself is a test question. So the receive relay shorts this point to the ground. And the next quarter wavelength section here acts as an open circuit. This quarter wavelength section there acts as an open circuit. So the whole entire setup is like if you have a pair of scissors and you cut the bottom half off and you drop it off. So then power from the transmitter goes through this reverse connected diode, which it does not matter for AC. The radio frequency would go through it both ways, would travel through a half wavelength section, 1/4 and 1/4. And now a half wavelength section of coaxial cable, whatever impedance you have at one end, like 50 ohms, that impedance is repeated at the other end, like 50 ohms, to be a match to the antenna. So that was transmit. Now we want to receive. We change the polarity with the negative one. The negative 12 volts goes to the anode of both diodes. So both diodes are cut off. When a diode is reverse biased and it's cut off, then you can cut it out. So this reverse biased diode over the receiver lifts the short circuit from the receiver. This reverse biased diode in series with the transmitter breaks the wire, no RF can go through. So any signal from the antenna can go two ways. One way down to the receiver or a quarter wavelength line, or the other way up a quarter, a second quarter, and a third quarter. But when radio frequency travels odd multiples of a quarter wavelengths, for odd multiples of a quarter wavelengths, the signal returns into the same phase. So whatever comes down from the antenna over 1/4 wavelength section will be in phase with the signal traveling for longer 3/4 wavelengths. So the two signals in phase, they do combine, you have reception in your receiver. Is there a problem with this setup? No problem whatsoever, just it's frequency dependent. So this is not used in a wide frequency range ham radio, but you have from 160 meters up to 70 centimeters. Maybe this setup could be used on 70 centimeters only, because how long should those coax sections be? For the HF frequency of 40 meters, you would need 10 meter sections of coax all coiled up. That is silly. So for 70 centimeters, 1/4 wavelengths would be 17 centimeters of coax, even multiplied by the velocity factor of 0.7. So it should be a really short piece. So this diagram is right out of your textbook, and take a note that it works fine and all right, but it's for a single frequency for a UHF band. Okay, next please. Never mind this illustration. If you would have an impedance meter, you could test quarter wavelengths and half wavelengths cable sections, short circuited or open circuited at the end. So let's just go to the very last part of transmitters. Here now there is a big confusion that Industry Canada created when they specify legal power limits for ham radio. We all kind of know that the basic license would give you a limited number of bands and a 100 watts ham radio. Well, surprise, ham radios are not categorized like that. So if we check for the transmitter power, then we have to go to Industry Canada government website, and there are all of the statements there. And one statement you read there about the power of a ham radio transmitter is that the transmitting power of an amplifier and so on cannot exceed the transmitting power by 3 decibels. What does this mean? Well, 3 decibels is twice the power, because 10 times the logarithm of anything 2 times, log of 2 is 0.3. Now, how do I know this from the top of my head? Are you supposed to know this too? It's a good thing to know it. Logarithm 10 base of 2 is 0.3. Well, I know it because I'm at it for the last 50 years. That's all. Other than that, if you just want to punch it into your pocket calculator, logarithm 10 base of 2 will be 0.3. So the decibel formula would be 10 times log of 2. 10 times 0.3, that's 3. Meaning each time your power doubles, say you have a 100 watt license and you have a 200 watt radio, are you legal? Well, Industry Canada says that somebody wanted to be very smart there, and they did not say that you are allowed to use power twice as high as your license. They said do not exceed by 3 decibels. So you have a 100 watt radio, you are legal. You have a 200 watt radio, you are legal, because 200 is 2 times 100. And 10 times log of 200 over 100, 10 times log of 2 is 3 decibels. So this is widely being abused, and if you read through, say, the American ham radio magazines, most amplifier manufacturers, they quote about their amplifiers stating that my amplifier can deliver legal limit. Meaning if the legal limit is 1 kilowatt, I sell you a 2 kilowatt amplifier and you are legal, because 2000 over 1000 is still just twice the power. 10 times log of 2 is still just a 2000 watt amplifier over a 1000 watt amplifier is 3 decibels off, that's all. So that's really an odd thing. Now, this 10.1 is a paragraph out of your textbook. Amateur radio operator certificate with basic qualifications allows you to, please bring this up about here. The holder of an amateur radio certificate with basic qualification is limited to a maximum transmitting power of, what is this 250 watts business suddenly? Don't we have a 100 watts license? So the keyword here is to read the input. The definition of input power is whatever DC power is being delivered by your power supply to your transmitter. So if you have 250 watts, say 25 volts and 10 amperes is being drawn by your ham radio, then 250 watts is flowing to your radio. And that's what they say. They do not say that you are allowed to put 100 watts RF into the antenna. They say that you may power your ham radio with batteries or with a power supply, and you may draw as much as 250 watts power from it. Why is Industry Canada so generous? Because somebody there knows that electronic amplifiers, they do have an efficiency. The higher the frequency, we are lucky if we get 50% efficiency. The lower the frequency on HF, the efficiencies of ham radios, they may go up to 75%. So you apply 75% efficiency to 250 watts, you will get much less power on the RF output of your amplifier. We read further, and please bring this up here. A 190 watts carrier power for transmitters that produce any other type of emission. And here, 560 watts peak envelope power. Now what is this? We hardly earn a basic license. We thing we are licensed for a 100 watt transmitter, and Industry Canada tells us that we can use 560 watts peak envelope power. Well, this is bewildering. 190 watts carrier power is produced in an amplifier which is drawing power from, say, a 12 volts battery or from a 12 volts power supply. Just wonder, what is the efficiency of one such amplifier? 190 divided over by 250 watts multiplied by 100 equals 76%. So when Industry Canada defines our rights, they are so devious about it. In my opinion, it would be simpler if they would say that since in all likeliness your amplifiers have an efficiency no better than 76%, that's what we allow you to use. So the 190 watts carrier is plainly 76% of the 250 watts allowance of power drawn from the batteries. And then you know that there are modes again. In CW, you press the key to transmit. In AM, you select AM, you are sending the carrier away. But as you talk to the microphone, you put power into the sideband, so your power increases. If you select FM, by selecting FM, you instantly transmit. Say you turn up the power dial on your radio. In FM, you instantly transmit 190 watts if you draw 250 watts power from the power supply. And that is well within our limits. So let's go up more to deal with the 560 watts. If we have advanced certificates, well, it's just as complex. Direct current input of 1000 watts to the anode. Or where the radio frequency output power measured across an impedance matched load, we are allowed 2250 watts peak envelope. It's bewildering again. So you have an advanced license. You buy a kilowatt amplifier. Meaning of that is that you are allowed to draw a kilowatt power from a power supply. Suppose you operate a kilowatt amplifier in your car, then you need a big power supply because a kilowatt is pretty well 80 amperes from 13 volts. So you have a kilowatt power drawn. You run your engine to be able to steadily draw 80 amperes from your batteries to put the kilowatt into your amplifier, and suddenly, magically, you are transmitting 2250 watts peak envelope power. How come? How did 1000 watts turn into 2250 watts? Well, I have an illustration coming up. What is the meaning of one? It's 750 watts carrier power for transmitters that produce any other type of emission. Any other type of emission would be FM. So how come that a 1000 watt transmitter can transmit 750 watts FM? It can transmit 2250 watts single sideband. So one up please. To illustrate all this, here is a typical ham radio power supply. For a low power radio, this ham radio power supply, 13.6 volts or so, would feed some 20 amperes or in the neighborhood of that to the whole radio. Well, those 20 amperes, not all of this power goes to the final. Some power goes to auxiliary circuits, some power goes to the receiver. That share of the power does not matter. Just as much as 250 watts can go to the power amplifier. And that power amplifier can output on 190 watts carrier or 560 watts peak envelope power. So the little up is disappeared. So what goes to the receiver and what goes to the auxiliary circuit does not matter. Again, 190 over 250 would be a 76% efficiency. And now the final diagram that would explain the 560 watts in single sideband mode. As we talk to the microphone, power goes up if you speak up loud, power goes down, and power goes out totally in between syllables and in between words. So what Industry Canada says that for a short split fraction of a millisecond, when you speak up at the peak of your voice, the peak power can jump up to 560 watts. But because human speech has pauses between words and pauses between the syllables, then if you take the average of this single sideband transmission, the average would come down to whatever they indicate, 220 watts or so. So this is how power is being specified for ham radios, and the quote-unquote 100 watt ham radio really is a radio that may draw 250 watts power from a power supply, may output 75% of that as a carrier on carrier-based modes for the duration of the dit or the dash in Morse code or for FM, and it may output 560 watts for a split second on the top of the modulation peaks. Okay, now we are done with this, and please turn this off and put up the receivers because time is short. We will return to this the next time when we have a review session. You can ask any questions. I want no longer to review this store and go right now because I'm worried about the short time we have for the receivers. So let's start talking about the receivers. Receivers, they may be in a separate enclosure and the transmitter is in a separate enclosure, or both may be together. Now we treat receivers as if they were separate. A receiver is connected to the antenna. Remember from the last slides of the transmitter part that the antenna is connected to the transmitter and the receiver by a relay. So that's how the receiver is connected to the antenna. The antenna, however, this is a small antenna, so it would capture UHF frequencies really well, but immersed in space. So transmissions coming from all around would produce radio frequency voltages in this antenna. So the antenna alone is not capable to separate signals coming from a variety of sources. But you want to make a ham radio contact. Suppose you work a UHF band on 70 centimeters and you point your antenna in a particular direction. You want to make a point-to-point contact, and you really don't want to pick up anybody else's transmissions. But the antenna cannot help because the antenna has a beam width. It would pick up anything coming from a direction within the beam width. So therefore, the receiver must have a circuit to provide selectivity. The desired frequency must be selected from all of the waves. The antenna captures a large number of waves, and we must select only one of interest. The selected signal will be very weak. Signals we'll get from the antenna are pretty well 1 microvolt or even less than that. When you read through a magazine, pretend you want to buy a new ham radio, then the manufacturer would always specify that the sensitivity of my radio is 0.5 microvolts or 0.2 microvolts. The lower the microvolts are, the more money you need to pay. So 1 microvolt would be a decent radio, but not extremely sensitive. And the input is always 50 ohms. Why is that so? Well, you want to transmit and you want to put your 560 watts peak envelope power into the antenna. The only way that transmit power goes into the antenna, then your radio and the coax and the antenna, they are all matched to 50 ohms. So because you absolutely need an impedance match to transmit, then you already have an impedance match, you might as well take advantage of it when you receive. A receiver would not get destroyed by an impedance match. So if you have just a wire running from 3 to 3 and you hook up another wire in the format of a T and you lead that wire down to your radio, you will hear all kinds of signals, but you could not transmit into it. So on the transmit, impedance match is a must. On while you are receiving, impedance match is a great feature, but you already have it implemented to be able to transmit. So when your receiver is also impedance matched, then there is a receive advantage as well, because the receiver also benefits from maximum power transfer between the antenna and the receiver. Power that goes into the radio is voltage squared over R. So the power is extremely small. Imagine 1 microwatt squared divided by 50 ohms, or even a top ham radio with a sensitivity of 0.2 microwatt, 0.2 times 10 to the minus 6 squared divided by 50. We are talking about a fraction of a picowatt. So the receiver must be very sensitive. The information carried by the radio wave, most commonly in audio signal, must be recovered. Now your radio would pick up in the same time sideband, AM, and CW transmissions from all over the place. But you only want your radio to decode only one at a time. So you select a particular mode. So the receiver, by the virtue of having a mode selected, the receiver now turns on circuitry capable to recover or detect or demodulate intelligence at the mode you selected. So we have different circuitry to recover from FM, from AM, from single sideband, and from CW. This information, the audio signal, then after it's recovered, it must be amplified. Because you want to drive a speaker, and to get a real loud big signal in a speaker, you need no more than 2 watts. To just have a soft signal in a room where you are alone and there are no other sources of noise, 100 milliwatt is sufficient in a speaker. Often you turn the volume on because the signal you are receiving is weak and you still want to hear it better. But no more than 2 watts is ever needed on the receiver audio. The amplified electrical signal must be converted into sound waves. Of course, then we need a loudspeaker or headsets. Headsets are often more advantageous than loudspeakers because the headsets, they seal to your ears and they lock out the room noise. So for weak signal work and reception, you need headsets. If you receive a great signal, then speakers would do. Receiver terminology up, please. What is the sensitivity? The sensitivity of a receiver by definition involves a signal to ratio of 10 to 1. Signal to noise ratio of 10 to 1. When your antenna picks up a signal, the antenna also picks up noise. Noise is coming from external and internal sources. The external noise could be noise from nature or man-made noise. Internal noise is noise your receiver makes, receiver itself. So all of the noise components combine, and you need a signal that is 10 times more powerful. So if you actually have your audio amplifier turned up to 2 watts, then 200 milliwatts could be the noise power, and over the top of that the audio signal would be 2 watts. So the ratio of 2 watts over 0.2 would be 10 to 1. So the signal to noise ratio, the better, the higher is the better. The telephone company, they fancy themselves that they provide 33 decibel signal to noise ratio. Time by time I throw in a decibel example because decibels are extremely important, and you will see decibel questions on the test. What's the meaning of 30 decibels? 30 equals 10 times the ratio of something. Well, if this ratio is 1000 times, what is logarithm decimal based of 1000? This is really easy. 1000, otherwise it's 10 to the third power. So logarithm of 10 to the third power is the power itself, it's 3. So 10 times log 1000 is 30 decibels because 10 times 3. If two power levels are in a ratio of 100 to 1, 100 is 10 to the second power. So log of 100 is 2. So now I just described 20 decibels. So the telephone company says that for my customers, I give circuits as good as the signal to noise ratio of 33 decibel. Now this is easy to compute without touch a pocket calculator, because we know that 30 decibels is the signal to noise ratio for a signal 1000 times more powerful than the noise. And then we also know that each time you double something, the logarithm of 2 is 0.3. So if the signal to noise ratio is whatever, but you double it, then it just goes up by 3 decibel. So if 30 decibel is as good as 1000 times over, then 33 decibel would be 2000 times over. So an average telephone line would give you a telephone signal in your telephone headset as good, and the noise you hear is lesser than 1/2000 part of the signal of the voice you hear. Okay, so the next feature of a receiver is selectivity. That's the receiver's ability to separate two closely spaced signals. The electronic device that provides selectivity to the radio is the filter. Band pass filters are used, and band pass filters will allow the passage of only a certain given selected frequency. Frequencies higher and lower are rejected. So sensitivity is for a signal to noise ratio of 10 to 1. Selectivity is provided by filters. And the third feature is cross modulation. Now cross modulation may occur when you pick up a very powerful local signal. A ham radio operator down the street in your vicinity, and he would put out a real large signal, and that real large signal would overdrive the amplifiers of your receiver. If an amplifier is overdriven, an amplifier tries to increase and increase and increase the amplitude of a signal, but it cannot increase it higher than the supply voltage. So if you have a 12 volts power supply, how would you amplify a signal to 100 volts? You can amplify within the capabilities of your power supply. So the amplifier starts clipping, and when you clip a signal, you create harmonics. So this is the mechanism of intermodulation or cross modulation. Attenuators are used as at the input of the ham radio receiver. There is a switch or a dial, and you turn that and you insert 10, 20, 30 decibels of attenuation. So insert a 20 decibel attenuator. The meaning of that is that whatever is coming down from my antenna, I make it weaker 100 times to not overdrive my radio. Image frequencies are kind of hard to understand. We'll return to it a little later after I showed you the block diagram of a radio. Stability and drift. This is just as important for a transmitter. Stability and drift depends on the goodness of your frequency synthesizers, crystal oscillators, direct digital synthesizers you have in the radio, that the frequency of your radio cannot move away. because somebody maybe transmits a perfectly stable signal. And if your own radio is not able to track it, you experience drift. Drift is also experienced if your radio is perfect and the transmitter is drifting. But there is nothing you can do about that. It is not your fault. But at least your own equipment cannot drift, so we will use crystal controlled, highly stable synthesizers and direct digital synthesizers. About 1000 Hertz is the most drift one can tolerate. If you receive a single sideband signal that drifts away even by 100 Hertz, it starts to sound like Donald Duck. It's hard to really decipher it. So 1000 Hertz maybe is tolerated for AM, and for Morse code it's tolerated in a rare situation when there is no other signal on the band. Then if your receiver drifts away, then the Morse code just sounds with a higher and higher pitched tone. So if there are no other signals to interfere, then you may even detect it that way. I think now is the time to take a break.
I have to.
Let's take a break and no longer than 10 minutes. Oh, my friend.